So in this video, we're going to talk about multi-slit diffraction, which is something that we already kind of touched on in SL waves when we talked about the Young's double slit experiment, which is pictured over here, okay? So we've already seen it, we've already encountered this formula for predicting the separation between the maxima in a diffraction pattern. But in the higher level section, we're going to be talking about multi-slit diffraction, so we're going to review this, as well as diffraction patterns formed by multiple slits, not just two, but we can say hundreds and hundreds of slits that are separated by the same distance. So to begin with, I'm going to make a few of these videos, and the first one I want to do is I want to review how we can derive this formula, and a new one that you're going to be using a lot, d sine theta equals n lambda. We've already encountered it for single slit diffraction. You can also apply it for multi-slit diffraction. So you're going to be able to derive these formulas using your knowledge of constructive interference. That's what happens in multi-slit diffraction, as you saw in videos that I presented in this workshop, and how we can create these formulas using geometry. Okay, so that's coming up next. So just to review, these openings are slits, and they're separated by a distance of d. That's what that d represents. And this would be your screen, where you're projecting the diffraction pattern, which looks like this. And if you remember, that's our central maximum, and these are the orders. Okay, these are the constructive interference for double slit interference. And these would be minima, which are zones of destructive interference, okay? This angle here is my angle of diffraction. X represents the distance from the slits to the screen, and Y represents the separation between the middle of a central maximum and the next, in this case, first order maximum, second order maximum, and so on. Notice that the intensities drop in a double slit experiment. Okay, so if you go back to the waves unit for SL, you would have a video there that showed us how we got this formula. Maybe the symbols are a little bit different. I matched the symbols to the picture that I have over here. But it's good to have different symbols so that you can try to think about what they actually mean. All right, so you can see this formula relates to the pictures that we have over here. So what we're going to do now is we're going to try to use geometry and interference to derive both of these formulas. How can we come up with that? And that's an important thing that you're going to have to be able to do on the IB exam. It often comes up where you have to show using a drawing or a geometry diagram how to derive these formulas. How can we make these formulas to explain the pattern that we see here? Now, just to really point out, the main difference between multi-slit diffraction and single-slit diffraction is that this formula here represents constructive interference for multi-slit, and it would represent destructive interference for single-slit. That is a super, super, super important thing to memorize, okay? So d sine theta equals n lambda is constructive interference for multi-slit diffraction, okay? That's important, and we'll show that in a second. All right, so how can we use geometry and interference to derive this? So let's just go through a little bit of review. Okay, if I look at just a clean diagram over here, and I'm going to change the color to something that is different than what the colors that are there. So what I have two wave sources, okay? The waves are approaching and creating wave sources from these two slits. And of course, if those two waves meet at the center, the path length is exactly the same, it's identical, and therefore those two waves are going to meet in phase, okay, which means that a crest is going to overlap a crest and a trough is going to overlap a trough, and we have constructive interference. That explains why we have a very strong central maximum, because the waves necessarily have to meet in phase because the path length is exactly the same. So that's why we would always have a constructive interference zone over here. But to explain how we get the next constructive interference zone, which would be to the first order maximum, if I would draw the path length from one slit to the other, we can see that the path length is different, okay? This second one is longer than the other one. So these waves would travel an extra distance than those waves. And because it's constructive interference, because I'm making an actual bright spot, they have to be meeting in phase. So there is a path length difference. And that path length difference has to be a whole wavelength. Okay, so whatever this travels, like if I draw a line here that intersects at a 90-degree angle, that's my path length difference. Okay, that's going to be just that extra little segment over here is going to be my path length difference. Okay, and that path length difference has to be a whole wavelength. For the first order maximum, it's going to be one whole wavelength. For the second order maximum, it's going to be 2 wavelengths. For the third maximum, it's going to be 3 wavelengths, and so on and so on. Okay, so that's how the geometry is explaining us. Okay, so if I take a look and I draw, remember from the video I showed you in SL, if I draw a triangle here, which I'm going to expand using a different color. So if I draw a triangle, here's my right triangle. This is going to be my path length difference, which is going to be n lambda. That's my path length difference. Okay, that represents this side over here. N represent which order. So in this case, it's going to be 1 for the first order, but that's n lambda. And this side here is going to be d, and this is going to be theta. So if you remember from the video I showed, that's a very important triangle. Okay, and according to this triangle, if I label all the sides of that triangle, this is adjacent, this is opposite, and that's hypotenuse. So according to trigonometry, I would have n lambda, which is opposite, over d is going to be equal to sine theta. Okay, because opposite over hypotenuse is sine theta. Okay, if you remember that. So already we're deriving an interesting formula for my angle of diffraction, because if I just rearrange this and I cross multiply the d with sine theta, I will get n lambda is equal to d sine theta, or just change that order so that you can see d sine theta is equal to n lambda, and there we have our diffraction formula. Okay, so this formula explains for multi-slit interference that this is my angle of diffraction. That's this angle over here. Okay, so that's theta over here. That angle, the angle of diffraction that we can measure between the center of the central maximum and the first order maximum, if I drew a triangle and I measured that angle, that's what that represents. D times sine of that angle is going to be equal to n lambda, where n is equal to 1, 2, or 3, depending on the order of maximum. All right, and we derived that formula just by the path length difference, the geometry of measuring that path length difference. Okay, and that's where this formula comes from. So d sine theta equals n lambda is actually a formula that I should have presented, or I could have presented for the SLs, but they don't need to know that. Okay, but that's the most generic and basic formula for diffraction. And it works out for multi-slit diffraction, that's constructive interference. But for single slit diffraction, this formula, as I showed in the previous videos, is destructive interference. Okay, so the question I have now is, how does this formula relate to this formula? Because these two formulas are actually the same. Okay, so that's what I want to look at now. So how can I take this formula and turn it into that formula? Well, it so happens that it's pretty easy. Okay, in an actual experiment, when we would project this pattern on the wall using our diffraction pattern, okay, I'm just going to erase all this stuff so we can see it a lot clearer. But in an actual experiment, when we would project this image on the wall, what the student would do is they would measure the distance between the middle of the central maximum and the middle of the first order maximum, and they would measure the distance between the screen and the wall, and that would give them those 2 dimensions of this triangle. Okay, so here's my first triangle. Okay, and those dimensions, y over x, is going to be equal to tan theta. All right, so I would be able to solve for my angle of diffraction between the center and the first order maximum by measuring y, the separation between them, divided by x, which is going to be equal to tan theta. Now, it so happens that at very, very small angles, if you work this out in your math class, you would find out that y over x is equal to tan theta, but it's also equal to sine theta at very small angles. okay? And then at very, very small angles, if you tried to do this on your calculator, you would also find out that y over x is equal to tan theta, which is equal to sine theta, but it's also just equal to theta, okay, at very, very small angles. Okay, so that's an important identity to know. Okay, so I can take this identity that y over x is equal to sine theta, okay, and I can plug it into this formula. So let's take a look at that. So y over x times d is equal to n lambda. So all I've done is just plugged it into that formula. And then what we would see is that if I rearrange this formula, okay, so y is equal to n lambda x. I don't know why I'm changing the colors here, but over d, okay? And that is exactly the Young's double slit formula, which has allowed us to calculate the separation between the maxima, depending on the order, if that's the first order, second order, or third order. That's what n represents. Lambda is the wavelength of the light going through. X would be the separation between the slits and the screen, and d is the slit distance. Okay, so in the SL formula, they didn't have to use any of these angles. They just apply the measurements. But at HL, you should be able to explain how both of these formulas are created. Okay, so just as a quick review, what we did in this video and what you should be able to do is you should be able to explain the geometry and interference that occurs to create this pattern when you have multiple slits. And the most important thing to understand in comparison to single slit diffraction is that multi-slit diffraction is constructive interference. There's two formulas that we can use. This formula applies to both types of diffractions, and you have to be able to explain it using geometry, and that is done by looking at the path length difference. Okay, so by analyzing the path length difference, which by drawing those lines here and then finding that intersect, you would see that that triangle represents the path length difference with respect to this angle. And this angle that would be formed on that path length difference is the same as that angle. They're similar triangles. Okay, so that's my angle of diffraction. That's my path length difference. That's the slit width distance. Okay, and that allowed us to derive this formula. And this formula allows us to derive the Young's double slit formula down here by making that assumption. Okay, it's worth practicing. It's worth putting on a cue card because this could be a 5-mark question on your exam.